The title is Quantum Toric Degeneration of Skein Algebra.
Thank you. I want to thank the organizers for inviting me for this conference, which is shaping up as another great conference in Vietnam. And the title may sound very fancy, but the talk will be mostly elementary. In fact, I will start with an announcement. So with my student, Robert Tuzon, we verified the Jones conjecture up to 24 crossings. And the Jones conjecture says that the Jones polynomial distinguishes all nodes, non-trivial nodes from the trivial one. So. Up to 24 crossings. Can you see me from the back, by the way? Is it okay if I write like this?
Does this mean same as detector? No. This is the same as detector? No.
Yeah.
No, it's not stronger. Is it stronger than detector? No.
Detector or not? Yes, that's the same. It's the same, yes. Okay, so I presume you guys can see from the back. If not, let me know. And this was a large computational project which required testing, I believe, over 10 trillion node diagrams and writing a lot of code and so on. All right. So now let me move to the main business. So let S comma M be a marked surface and so this S can be oriented or not, with boundary or not, and marked means that this set M is a finite subset of the boundary of S. And we're going to study tangles in that, so that T as M be the set of framed tangles in an oriented I bundle over S. All right, so we take, well, I is the unique interval. You take I bundle over S, so you get orientable three-dimensional manifold. You consider tangles in it, which means embedding of one manifolds, that is loops or unions of loops and intervals. And they are framed, which means really we're talking about annuli and little strips of paper, like rectangles. And we require that the boundary, well, we require that the boundary of a tangle lies in the boundary of S. In fact, not just that, but that it lies inside of M, fibers over M. All right, so if the bundle is orientable, if S is orientable, then this is just trivial bundle S cross I, so then it would lie in M cross I. So that's one possible approach to what we're going to do. But in fact, there are two approaches. Another approach, which will be sometimes useful, is that we will take those endpoints of a tangle which lie in the fiber, and we choose the direction, and we're going to project them onto S. And the reason it's useful is because then we really can talk about tangle diagrams. Okay, so
What is M of M cross I? You mean boundary or?
well, M is a finite subset of the boundary. The endpoints of T should lie in the fibers of the points of M.
Oh, okay.
If the boundary is trivial, it's just M cross I.
Sorry. Okay.
So if we cross, well, if we project, so sometimes it's useful to take those endpoints and just project them onto S, and then what happens is actually the boundary of T, you can think of it as lying in the boundary of S minus the base points. Frankly, it's mostly a remark for experts. It doesn't really matter. Those details will not really matter for that. If it's confusing to you, it doesn't really matter that much.
So it means that in the first case, the because T here is actually the you consider it as a ripple, right? So it,
Yes. So I also should mention that the framing here should be always horizontal.
always horizontal.
Yeah, that's right. At the endpoints. Anyways, in this approach, you just think of it as tangle in S. So now, so really now tangles represented by diagrams in S, and they always have horizontal framing.
So you don't allow half twist.
Correct. Yes. Yes. Yeah, that's another technicality, but really, I mean, it's not essential for understanding the main ideas of the talk. So now I want to fix a ring R with a fixed invertible element, a Q. Sometimes it is denoted by A. All right, and now I'm ready to define the Skein algebra.
And you can also use that one.
Okay, maybe it would be more convenient to put this one.
Right in the middle here.
Well, maybe like one next to another, because I see there's another one.
Yeah, maybe we move this one.
Okay, exactly. Then you can use this one.
Yeah, we need.
Can you actually lift it on the
Okay.
Wow.
Maybe we can now use both. Thank you. All right. So now, with these definitions, we can define the Skein algebra of S. Will be another S. This is for neither is for my last name. This will be for the Skein. Yes. So by definition, it's going to be the space of linear combinations of tangles with coefficients in R. This is a very large space. So we're going to quotient it by the Kaufman bracket Skein relations. So quotient that by, which are these. Whenever you have a trivial loop, so unknot, well, it's going to be equal minus q squared minus q to minus second. This is the standard definition of Skein algebra. However, I'm going to add one extra relation, and the relation says that if you have two endpoints and an arc like this, so this is a fiber over some point of M, then you have something like that. In the approach A, in B you have to think about it horizontally, but if you have that, this is equal to 0. So this is a slightly reduced Skein algebra. So why this is an algebra? Because if you have two tangles, you can always stack them together, one on top of the other, and this is their product. If you use this approach number B, then you have to be careful what happens with the endpoints. If you projected the points of the fiber to your left, say, then T1 times T2 is a union of them with the endpoints of T1 to the left of T2. Frankly, it doesn't matter whether it's to the left or to the right. You just need to fix one convention, and then you get an algebra which is independent of your choice.
So if your surface is not oriented, then what is the vector?
Well, so yeah, so to do this, you have to decide which side you project those endpoints, and so you just decide it somehow. You can put it as part of the structure. The point is, it doesn't matter at the end. You get the same algebra. But again, this is really a technicality.
Could you give very simple picture of approach A and B? Is it difficult?
You know, yeah, as I said, my first advice is just not worry about this because it's really technicality. But okay, let me try to draw something. Let's see if I can manage to draw anything. This is part of the boundary of S. This is I. This is point in M. You know, you may have something like this. Some arc number 1, arc number 2. And then you have this point M here, and then, well, you just projected things, so it's like this. Again, I cannot stress this enough. It's really technical. Don't worry about this. This is maybe for people who think about it seriously and work on Skein algebras and care about details like this.
But this is the same as the Muller, what Muller defined, right?
Well, it's almost like Muller's algebra. It's 99% like Muller's algebra, but it's not exactly.
What's the difference?
Well, the difference is that first of all, the difference is that he requires that square root of q is in a ring, and I don't.
But that is just for, well, actually, you can define the Muller's algebra without.
Well, he has a relation like this.
Right. Yeah.
That this q to 1/2 equals.
Right.
But
yeah. But it doesn't matter, right? You can just remove this and then it's just there.
Yeah, correct. Correct. Yes, and it's the same as my algebra with Przytycki, almost, also almost. But we use a little bit slightly larger reduction there. Yes.
Yeah.
Yes.
Oh no, the Muller's one is exactly this one.
No, well, by definition, not because we hear
No,
requires.
but this is just for convenience. This is just normalization of the one that you split.
Okay, yeah, that's yeah, I agree. And it's almost, as I said, also the one with Przytycki, but this is slightly smaller reduction. But again, it really doesn't matter if you choose Muller's or mine with Przytycki. It's all fine. Anyways, why? Well, yes. Well, Skein algebras were invented, I should say, or introduced by Vladimir Turayev and Józef Przytycki. But there are many people who work on them, including people here. Tank, Francis, Helen, whom I miss? Oh, of course, Joanna. Yes. And probably I missed still somebody. All right, so yes, we're going to talk about them. And perhaps I should tell you why do we care about them for those who never heard of this before. Well, first of all, the first theorem is that they are always finitely generated. Well, to be precise, it's finitely generated in the pi1 of S is finitely generated, so for a finite surface. And most of you know this, but just in case, let me say that when Q is equal plus minus 1, this turns out to be a commutative algebra. Why? Because you have this relation, and if you rotate the pictures 90 degrees, you have this rotation, this relation. Yes, and now if Q is equal plus minus 1, they're equal. So it can change crossings in the algebra. In a sense, it means it becomes a very bad knot invariant. Sort of that maybe the initial point, motivation for all this business was to have a knot invariant of knots or tangles in thick surfaces. It becomes very bad knot invariant, but now it becomes commutative, and well, it's an old theorem. Yes, it becomes commutative because it doesn't matter now whether T1 is on top of T2. Oh, I have to be a little bit careful. So, okay. I should say, okay, so for Q equal minus 1, it's commutative, and the Skein algebra, at least with the empty set of marked points, becomes the coordinate ring of character variety of S. Character variety is the set of all homomorphisms of pi1 of S into SL2C. So this looks very unexpected, and I guess I'm not going to explain this, but this is the set of all homomorphisms up to conjugation by SL2C. This is called character variety of S. It's an algebraic set. It has coordinate ring. Turns out that this is equal to that. Actually, I shouldn't worry here. So this is true for plus minus 1, yes. And this is old theorem of Bullock and Przydicki and myself. And in fact, the isomorphism between, so in particular it says that those algebras are isomorphic for Q equal 1 and minus 1. That's not obvious. That's a consequence of spin structure, of existence of spin structure on this oriented I bundle. So you see that, what do you see out of this? Well, that somehow those Skein algebras are quantizations or quantum deformations of the character varieties of surfaces. And so you can think of this character variety of a surface as complexification of the Teichmuller space. Okay, and here what we get is a quantization of character variety. So what's really S is, you can say, is quantum Teichmuller space. And this may sound very far-fetched, but in fact, there's another model of quantum Teichmuller space for punctured surfaces due to Chekhov and Fock. And there is a work by Francis and Helen who showed that Skein algebras for puncture surfaces are very closely related to that Chekhov-Fock quantum Teichmuller spaces. So this you can think of another model of quantum Teichmuller space with the advantage that actually is defined also for closed surfaces, even for marked surfaces, but for closed surfaces, and I think this is the only model for closed surfaces. So that's one motivation for studying those things. Another motivation is that Müller proved that those guys, in fact, even more generally these guys, after some small localization, become quantum cluster algebras. So they have some very interesting underlying algebraic properties.
For closed surface? Or
No.
surface?
For
Oh.
also all marked surfaces with localization of boundary arcs. All right, and finally I should say one more thing. So this is for no marked points, but with marked points, maybe I should keep this. So with marked points, you have similar kind of equality. So let me say how this goes. So now let x of s comma m be the set of all symplectic flat C2 bundles over S. So this is a little bit more fancy stuff perhaps, with a choice of section over M. And then you can prove this is again algebraic set. This was done by Samuelson and Müller. And you can prove that that the Skein algebra of now for any m, this is the coordinate ring of that. So I believe it's done by Yutang. Can I say that, or do you prove something slightly different?
Almost the same.
Okay. Well, in any case, I have another proof of this. I think slightly different than Tang. Yes, for q equal 1. So again, you get Skein algebra is going to be, in this case, for any m, is going to be some quantum deformation of some moduli space of presentations. But again, the details of this will not be important. Because really, I want to talk more now about Skein algebras. This was more like a survey of what they are. So I am going to study those algebras, which, as you can see, are quite interesting objects, using the Thurston's theory of measured foliations. Okay, so let F be a foliation of S. What does that mean? Well, it means it's the composition of the surface into one-dimensional manifolds, loops, intervals, infinite lines, such that every point, well, has a neighborhood which just looks like this locally, so it's locally trivial. Well, for Euler characteristic reasons, we couldn't live just with that, because you wouldn't have a foliation like that for surfaces with negative Euler characteristic. So we allow for singularities. And so we'll consider k-prong singularities, like in Thurston's theory. This is an example of a three-prong singularity. But in general, we consider k-prong singularities with k at least 3. All right, so we have that. So now I can define the something which I will denote by h of f, and this will be, well, I call it the transverse monoid of f. What's that? Well, it's the set of all multi-curves in f which are transverse to the foliation. All right, so what is a multi-curve? It's like a tangle diagram, but no crossings, with no crossings. Everything, all the curves inside, meaning loops and intervals, have to be transverse to the foliation. In particular, they cannot hit the singularity. And now I claim that this set is a monoid. Why? Because, if you have two, maybe I'll take this one. Well, if I have a foliation and I have two arcs, then this crossing has two smoothings. Like that. And one produces always arcs which are transverse, at least locally. Yeah, good point. And another one produces two arcs which are never transverse. So this is transverse smoothing. Okay, so now this is a monoid because for alpha and beta in this set, alpha plus beta is just a union of them with all crossings smoothed transversely. So you get another, in this way, the result of this operation is another multi-curve transverse to the foliation. And by the way, we allow here for the empty set in this H. So it's a monoid with identity. And it's a curious little thing. It's like first homology. You know, its elements are combinations of loops and arcs, but they're all unoriented. Yes?
Is it obvious it's associative?
Almost obvious, yes. And commutative. Well, yeah, it's actually, it's totally obvious, yes. I mean, if I take the first multi-curve, second one, and the third one, I can first resolve the crossing between first and second, and then with what is left with the third one or in other order, at the end of the day, you just resolve everything. So it's like first homology, except it's built of unoriented cycles. And in fact, this analogy goes further, because let's see. Because if I have two arcs, alpha and beta, well, they can intersect either this way or this way in terms of the foliation. So I can define sign. I can define sign of the intersection. This is +1, this is -1. We are used to defining signs of intersections of oriented arcs, but in the presence of foliation, we don't need orientation. All right, so what does it mean? It means that now we have a form on H. Okay, so this, by the way, this H then is related to the fact that this is like homology. So we have a form on transverse homology which sends, unfortunately this is not erasable. Alright, so it goes to Z, which sends alpha and beta to their intersection number. Signs of crossings between alpha and beta. Okay, so it's a skew-symmetric form. I want to say almost bilinear, but I have to be precise. It's bi-additive skew-symmetric form. All right, so this goes. So now I will need this gadget. Now I will need this gadget later on. R, H, S, M. In fact, I'm going to put here omega. Okay, this is omega. This is omega. What's that? This is like a groupoid ring. So it's a pre-R model with this basis given by that, but multiplication is twisted. It's a twisted groupoid ring, twisted by omega. So here multiplication is that alpha times beta is equal Q to power omega alpha beta times, well, alpha plus beta. This is going to be in H, yes? In the normal groupoid, multiplication would come from the monoid operation, but here I twisted it. It's a curious thing, we will need it. But, well, notice the following. What happens here is that now you have alpha and beta. Well, what's that? Well, this is going to be Q, something like that. So you can think of it as transverse. This looks like a Skein relation. You can think of it as transverse Skein algebra. All right, so we're almost ready to go back to Skein algebras, but not yet. So Thurston's foliations come with a measure, transverse measure. Okay, so what's transverse measure? Well, you can measure the length of arcs in the surface with arbitrary endpoints in the surface, and this measure is supposed to be invariant. So if I have an arc like this is some foliation here, leaf of foliation, another leaf of foliation here. This will be invariant under any isotopy of alpha, which keeps the endpoints in those leaves. Okay, so you can associate to that. You can associate to this a measure, which I will denote by nu, which will be a number between 0 and, well, it will be finite, so in this interval. So this is the measure. All right, so now with that I can come back to Skein algebras. Can I? Yeah, okay, so back to Skein algebras. Okay, so first of all, we need the following result. We need the fact that those Skein algebras have very simple basis to describe. So theorem, no. We'll get there in a moment. So, all right, so yeah, we are going to go back to Skein algebras. And the first thing I want to observe is that whenever you have a measured foliation, it defines a filtration of the Skein algebra. What's a filtration? Well, it's a family of linear subspaces of the algebra. So let's define those subspaces. So filtration. Well, for every real number, non-negative real number L, I'm going to define a subspace of Skein algebra, linear subspace, which will be spanned by tangles on tangle diagrams of length less or equal L. This is the transverse length, which is coming from given foliation, given measured foliation. All right, and so it's filtration because now FL, of course, is a subset of L, FL prime for L less or equal L prime. And in fact, it's not difficult to see that this is an algebra filtration. So what does that mean? So the mark FL, if you multiply elements from this one and this one, you will get elements in L plus L prime. FL plus L prime. And the reason for that is you have a tangle diagram here of total length L, so of course you have to sum the lengths of all components. And another one of total length L prime. The product is really their union, so the total length cannot be larger than that.
So the length comes from the Thurston's measure, right?
Correct, yes. And what's good about algebra filtration is that they define associated graded algebras.
Here L can be actually any positive real number, right?
Correct, yes.
But you use all the integers in order to define the associates one.
No, so I'm going to use all the real numbers. Yeah, so this defines associated graded algebra G, S, Sm, and as a vector space, well, it is a space of quotients like this. So what are its graded components? Well, for any real number, you can consider the space F sub L and quotient it by F sub less than L. This is another space, which is space of everything which has length, total length less than L. Okay, this is a little bit different than maybe what you saw as graded algebra, because usually graded is integral. Here it's not integral, it's real, but it doesn't matter. Yes?
Once again, what is the length again?
Transverse measure length.
So you don't need a transverse measure on the foliation to define that?
Well, I need it. Yes, yes.
Okay.
Yeah.
So are they non-zero? I mean these Fn over F less
Are they
than F?
non-zero?
Yeah.
Well, lots of them will be zero.
A lot of them will be zero. Most of them will be zero.
Yeah, it's a true statement.
And this depends strongly on the choice of the foliation.
Yes, because it depends on the measure, which of course wouldn't exist
Okay,
without.
also the structure.
What do you say?
Also, it's a topology of the foliation.
Yes, yes. Oh, you asked me if that is isomorphic for different foliations. So,
Yeah.
so
For example, if you have the right component.
well, I don't really have a theorem about that. There might be some isomorphisms, but yeah, I'm not sure. Well, yeah, I mean, we could go into this, but it's more complicated. All right, so we have, so this just defines it as a vector space, but the product then, it's what you expect. Well, you can just say the product of two diagrams is still union of them, one on top of the other. So it's an associated graded algebra. Yeah, we need to understand them better, slightly better. I be saving the paper? Should I use this side? Or? I don't know. Hopefully we have.
What do you think about the teeth?
Adam, I think you should just flip it over
Oh.
rather than.
Oh yes. Yeah. Sorry for the mess. All right. So now we can say something about those algebras, and in particular their bases. So the theorem is that every Skein algebra, graded or not, has a basis of of multigraphs. In S, comma, M. Again, what are those multicurves? Again, these are like triangle diagrams but without crossings. So the fact that this is a generating set is very easy. You take any skein, which is a combination of tangles, you resolve all the crossings in tangles, and you have a linear combination of multicurves. Proving that they are linear independent is always harder, and you can use, I can adapt the ideas of confluence theory. Confluence theory is usually used like in computer science for rewriting systems, but you can adapt it to the context of diagrams on surfaces, and using that you can prove that they are linearly independent.
Can I have questions? Return to this, the algebra structure of this associated grade algebra here.
Yeah.
So usually in the associated grade algebra, you have to choose, you multiply over the top degree part.
Correct.
But how can you define the top degree part here? Because
Well, this is the top degree part.
yeah, but so if you take an element, you need to choose the smallest L so that it's in there. That would be the top degree part. But
Yeah.
but does L exist because it's
Yes.
R? Yeah.
It always exists.
So it exists.
Yeah.
Yeah. So given any diagram, you can then there exists a number L, so that is the minimum for that one.
Yeah, so for every x in SSM, there exists LM, I don't know how to write the maximal, such that x is not 0 in f L divided by f less than L, Lm. I guess that's what you are asking for.
Yeah.
Yeah, and the reason for that is what are elements of S of this Skein algebra, finite linear combinations of diagrams. So you just take the length of the longest of them. Well, you just take the length of the longest of them, and this is your L sub m.
This is for fixed foliation.
Correct. Everything is fixed. Foliation and measure is fixed. All right. So yeah, I told you. Well, let me just say this. Confluence. That's the most important word in this proof. But I think many of you already have seen results like that, so this is not surprising. Okay, so now let's see. What else should I tell you?
Would you care to expand a little bit?
On this proof?
Yes.
Well, okay, so again, the fact we need to show two things, that those multigraphs span the Skein algebra. That's, I would say, easy, because if you take any element of the Skein algebra, it's a linear combination of diagrams, and you just resolve all the crossings of diagrams. You can always do that by the Skein relation. So you get linear combination of multicurves. Proving linear independence is harder, as usual. Yeah, since there's more stuff coming up, which is very important, maybe I would just skip like this, but the proof is basically similar to prove the classical case when S is oriented and M is empty, so, or when they are not reduced. So I can tell you more details in private here, because we didn't really get yet to to the quantum, neither, well, we didn't get to the quantum toric varieties at all so far. All right, so what does it mean? It means that really as vector spaces they're the same. Why do we consider graded version? Because usually it has an algebra structure which is simpler to understand. Number one. Number two, the original algebra structure usually is some deformation of this one. Well, by definition, it's some deformation of this one, and they share many properties. For example, their Krull dimension will be the same, and some other properties will be the same. All right. So now I'm going to study this algebra for a moment, and now I'm ready for main theorem.
What's
Yes.
Krull dimension for something which is not Z-grade?
Well, it's.
Or what's the Hilbert series of something which is not Z-grade?
Am I getting in trouble here? So I was thinking of just. I was just thinking of increasing chains of prime ideas. Yeah, two-sided prime ideas.
There is no Poincare series though.
That's okay. Well, frankly, this was just a comment. Yeah. But it is again. I'm happy to withdraw my comment. It was just really in the passing, because I want to get to the main stuff of my talk. So I want to now consider a certain type of foliation. So a foliation is open if it has no closed leaves nor compact separatrices. All right, so closed leaf is an obvious thing, it's just a loop. Compact separatrices, what's separatrix? Well, it's an arc connecting two singular points. All right, so I'm saying compact, well, basically means compact interval. I'm saying that I'm not allowing for such things here. This is my own term. Maybe it's known in literature. If it is known, what's the name for it?
Connection between singularities. Connection between singularities.
Yeah, sure. No, the separatrices is a known term, but for this kind of foliation, maybe there's some other term. I don't know. So, anyways, so this is open foliation, and
Can you say no compact leaf or
separatrices. So connections between singularities. All right. So now we are ready for the main theorem. Maybe I should move to the main board for that. All right, so number one, so for any S comma M, number one, this strange algebra, the twisted monoid algebra, is a subalgebra of the graded Skein algebra. Number two, if F is open, then they are isomorphic. All right, so this gives you some very explicit, I would say, description of what this graded Skein algebra is. It's that. If F is open. Number three. Well, let's say something about this twisted monoid algebra is a subalgebra of a quantum torus. What's a quantum torus? Well, it's like the algebra of the round polynomials, but they don't commute. The variables don't commute, they Q-commute. So it will be something like R. There will be some variables x1 up to xn, where xi, xj is going to be q to some power, which we don't care about. That's the quantum torus, and I claim that this weird algebra is a subalgebra of the quantum torus.
But it's just the definition, quantum torus, what you wrote there. You have any monoid. If you have a group and then you have that multiplication, then that is quantum torus. And so if you just extend this monoid to the home group, then you get the quantum torus.
Okay, first of all, you have to prove this monoid has conservative property. And so I claim it has conservative property.
Sorry, what
Oh,
do you mean?
so you mean that so that it embed in a group?
That's right. Conservative property means that alpha plus gamma equal beta plus gamma implies alpha equals beta.
So that you can embed into its quadratic group.
That's right. So first of all, I hidden this statement there. Second of all, you can embed it into a group. You can groupify it, but the group may be of infinite rank. So I claim it's of finite rank. But then you are right. You saw this through. That's what it is. Yes. And so in fact, I can tell you what the rank is. Where n is the dimension of the character variety of the marked surface. Yes, so n is equal, for example, 6g minus 6 for closed oriented S and M empty. All right. All right, so we have a theorem which works for, the most interesting part here, I guess, it works only for open foliations, which look quite exotic. So, it's not easy to come up, if you are foliating a surface, it's not easy to come up with actual foliation which has no circles, no closed separatrices. But I claim that they are abundant in nature. So another theorem says that if the Euler characteristic of S is less than 0, or S is punctured torus, then open foliations are dense. Open, I guess, measured foliations are dense in the space of the projective, in the space of measured foliations of Thurston of S. This is the space of measured foliations of Thurston.
But isn't punctured torus also has negative Euler characteristics?
Because it has 0, no? Oh, also. Yes. Why did I say that? Okay. Why did I say that? I don't know. Sorry. Jet lag. Very good. Okay, well, so what it means is that actually they are abandoned, okay? And with this few surfaces as an exception, they are abandoned for orientable and non-orientable surfaces. Very quick proof of that. First of all, if you have a surface like that, you can prove that there exists a pseudoAnosov diffeomorphism on it. Once you have pseudoAnosov diffeomorphism, you can take the stable foliation of it. Once you have stable foliation, the mapping class group acts on it. And
singular.
Yeah, they're all singular. Yeah. And acts on it, and every measured foliation in the orbit is also coming from pseudoAnosov. It's a stable foliation of some other pseudoAnosov. And then there is a theorem which says that the mapping class group action on this space or on the projectivization of the space, has dense orbits. So that's how we prove it. The bottom line is that plentiful, so there is lots of cases this theorem applies. All right, let's do this now. So let's talk about some corollaries to that. Okay, how many minutes I have? 0?
Minus 2.
Oops. Well, let me at least do one corollary. So corollary, well, for S as above, well, what is the Skein algebra then? Well, it is a deformed Skein, deformed subalgebra of a quantum torus. Okay, so this corollary tells you something about the very general structure of Skein algebras. Every Skein algebra is a deformed subalgebra of a quantum torus. Which subalgebra? Well, this one, yes. Well, so we have this isomorphism. So this is really also a subalgebra of the quantum torus. And what is Skein algebra? It's the formation of that. So this tells you the very general structure of what Skein algebras are. In fact, for puncture surfaces, we know that those algebras are subalgebras of quantum torus, again, by work of Francis and Helen, and also of Tang. But this is more, I guess, more general, includes also closed.
So the new thing is that, well, so this is just for closed surfaces new, right?
That's correct, yes. So this also gives you another proof that, well, not just another proof, but more general proof that these are domains. No zero divisors, because there are no zero divisors here. This implies no zero divisors here. Even if you don't care about anything quantum, this is actually new, because it tells you something about character varieties of unoriented surfaces, number one, which was never proved. The fact that they are reduced was never proved. And it sort of unifies all other papers which were proving versions of this for character varieties. And it's also new because of the mark points. And, well, I guess I will not get to the title of the talk. But I want to claim that, well, what are those guys? These are quantum toric varieties. Okay. Why? Because if Q is 1, these are toric varieties. So these are the formations of toric varieties. All right. So in particular, what this theorist tells you is that every measured foliation gives you a toric deformation of Skein algebra, and for generic Q, it gives you a quantum toric deformation. So I will stop here.
So any questions, comments?
I have a comment,
Yep.
not a question. It's a conference between quantum topology and hyperbolic geometry, and in general, the two people have a hard time talking to each other. So this is an example where, so you have a funny form omega for the hyperbolic geometers, that's known as the Thurston intersection form.
Yeah.
And that thing keeps popping up in papers of Helen and I, for instance.
Very good.
For us, it was just a computation. And so to some extent, you explained a little better.
And this is in the presence of foliation. We're talking about transverse arcs in the presence of foliation.
There is no difference between what you call an open foliation and an ideal triangulation. It's roughly the same thing.
Sounds very interesting.
That's one thing where the hyperbolic geometers.
But the difference is that I can talk about my open foliation for closed surface.
Yeah, the for closed surface.
For closed surface.
Yeah, that's
Oh,
yeah.
people.
Yeah.
People, I missed that.
Yeah.
So anyway, that certainly explains.
That's very good. I would be happy to
So,
understand.
so with Hagen, we use the Ferson intersection form a lot.
Okay, awesome.
And
And it's defined for, oh yeah, of course, so I should say, for example, that
I can explain to you.
Yeah.
It's a homological intersection number in the orientation covering of the foliation.
Sounds very good.
I gave you
Yes.
the keyword.
Yeah. No, that's very good. And I should say that one source of foliations is you have a punctured surface, you could consider ideal triangulation, and every ideal triangle has an obvious foliation, where the singularity is in the middle.
Yeah.
And I guess that's what you get.
That's my comment.
Yeah.
Any other questions, comments? So let me make a comment and a questions. So first of all, your algebra is canonically isomorphic to Müller's algebra, actually. So
Yeah, sure. Yeah.
Yeah, that's just the same thing.
My only counterpoint to that was Müller uses q to the power 1/2. So
It's just by normalization.
sure.
If you don't need the by normalization,
Correct.
then but the algebra is just the same.
I agree.
There's no
Modulo, that's one issue, I agree. Yeah, but I agree, yes. Yes.
So and the second one is so actually the grade algebra here, the grade components is
Yeah.
non-zero if and only if you have a multi-curve of that length, right?
Correct.
Just so it's just the length and what
Sure.
can you say about that set? So is that set
It's an interesting-
well ordered? You know?
No, it's not.
No?
It's not. It's not well
Because
ordered.
usually, to use that one, it's useful if you can do some induction. And you only do induction, if it's well ordered, then it's good. You can go down until you
It's
get
not
to the...
well ordered.
It's not well ordered.
Yeah.
Okay.
But it's you can say it's a subgroup, submonoid of R of finite rank. It's finite degenerate submonoid of. Yeah. Well. No. I would draw anything. It's not well ordered, but nonetheless, everything here I believe stands.
Okay. So, you have a question? So, there's no more questions, no less. Thank Adam again.